Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. We are discussing Unit 4. Unit 4 relates to hydraulic turbines. We have completed first starting from the components of a hydroelectric plant, classification of turbines, then afterwards the distinguish between impulse turbine and reaction turbine, distinguish between tangential flow, radial flow, axial flow, and mixed flow turbines. Then we have taken up the various efficiencies such as hydraulic efficiency, mechanical efficiency, and overall efficiency. Then we have taken up the components of a Pelton wheel and sketch. And then we have gone for work done and efficiency in the case of the Pelton turbine through the velocity triangles. So the last topic of the Pelton wheel is the working proportions of Pelton wheel and how to design a Pelton wheel. Design in the sense that we are interested in hydraulic design. So working proportions of the Pelton wheel, which is in other way design also. Then again, putting into steps what is the design of Pelton wheel that we will complete in today's class. So in today's lecture, we are going to discuss on the working proportions of Pelton wheel. Pelton turbine followed by design of Pelton wheel. Kindly remember that design in the sense that it is only the hydraulic design. So what are the various things? Please follow the order actually. Number one, the velocity of jet at inlet. Because how to calculate these things? All are known to us at some point or the other in the past. V1 is equal to CV into root 2GH. So generally in any problem, we will be given with the net head. So knowing the net head and the coefficient of velocity CV may vary between 0.98 to 0.99. If nothing is given, you can take it like this. And you can calculate directly what is the velocity of jet at inlet. So knowing H value and CV value, we will be able to calculate what is the V1. Then what is H is equal to, already I mentioned, net head. Then coming to second, actually, what is the velocity of wheel? When I say velocity of wheel, it is the tangential velocity of the wheel. Velocity of wheel u is equal to, because it is same at the inlet and outlet, u is equal to ku into root 2gh. Again, Ku is called as speed ratio. Speed ratio, this may vary between 0.43 to 0.48. Approximately 0.5. Previous one is almost 1. This is 0.5. So 0.43 to 0.48, if it will be given generally. If not given, you can take it and work out. So this is H net head again. So velocity of wheel is also can be easily obtained. Knowing only what are the things to be known, only the net head. CV value and KU value, if they give, take it, or otherwise also you can assume and go ahead. Then third point is the angle of deflection. Because when we have drawn the angle of deflection of jet through buckets, if it is given, you can take it, or otherwise it is generally 165 degrees. That means that is phi is equal to 15 degrees. So kindly remember this. Instead of 180, where we get 100% efficiency, here the angle of deflection is maintained as 165 degrees, and that phi is equal to that. In the semicircular vein it will be 0. Now we are maintaining 15 degrees here. This is the third point. And fourth point is, we can calculate the mean diameter of the wheel, mean dia of Pelton wheel, and this is also called as pitch circle diameter. Pitch circle diameter. This can be calculated using the equation. This is represented by pitch circle diameter. D is obtained from U is equal to pi d n by 60, where n is the speed of the things, speed of the wheel in RPM, n is the speed in RPM, right? U already we obtained by using the relation Ku root 2 GH. So unknown is only D. So therefore D is equal to 60 into U divided by pi into N. Given N, calculated U, you can calculate what is D. Once this D is obtained, then naturally the next one is what is the jet ratio. What is jet ratio? Jet ratio is, it is nothing but the diameter of pitch circle, in other words capital D, divided by what is the other one, actually the dia of jet. So this is D by D, and this ratio generally we call it as M, and generally we maintain it 12. For most of the cases we maintain 12. And then sixth point, is the number of buckets. How many buckets will be there on the wheel? The number of buckets on the wheel, Pelton turbine wheel, is equal to, which is represented by Z, is equal to 15 plus half of D by D. 15 plus zero point 0.5 into M. So this is the thing. So this is again where M is equal to what? Jet ratio, right? Over. Then last point, number of jets. Nothing to worry. Only thing is one or two problems. If you solve, all will come to your rate thing. This is total flow rate. Total flow rate, capital Q, divided by flow rate through each jet. Flow rate is nothing but discharge. Flow rate through each jet. Small q. So these are the 6 points. Again, shall we recollect once again? Number one is the velocity of jet at inlet. V1 is equal to CV root 2 GH. Net head will be given to you always. CV is 0.98 to 0.99. Even if you put, if though nothing is given, you can take 1 and then go ahead also, no issues. Then velocity of wheel, Ku into root 2 GH. Ku is speed ratio. H will be given. Ku is around 0.45. Then come to the angle of deflection is 165 degrees, and phi is equal to 15 degrees. Then pitch circle diameter you can obtain by using the equation U is equal to pi dn by 60, and then get the diameter. Then jet ratio is equal to capital D by small d. Capital D is the pitch circle diameter divided by diameter of jet. That will be generally 12 basically. And then the number of buckets is equal to 15 plus half of capital D by small d, jet ratio. Then number of jets is equal to total discharge divided by discharge through each of the jet. That is how we will get it. So come to the conclusion point. What do you mean by the design of Pelton wheel? Design of Pelton wheel, all this above only, but only thing is I will put it in order. Design of Pelton wheel means what we need to find out. Number one, we will be asked to find out what is diameter of jet. So from the given data, you should be able to calculate what is diameter of jet. Then you need to calculate what is diameter of wheel. Diameter of wheel at the top I have already given. This is second point they will ask. Then the third point they will ask is what is the width of the bucket? Width of the bucket. Width of the bucket is equal to, kindly note it, it is 5 into small d. And then fourth point is what is depth of bucket? Depth of bucket is equal to 1.2 times d. Then number of buckets is equal to 15 plus zero point 0.5 into m. You know it already. Where m is the jet ratio. This is nothing but capital D by small d. Right? These are the points generally we mean by design of the Pelton wheel. Only for your understanding sake, I will take a simple example so that you understand generally. It appears as if difficult, but nothing actually. Very simple things in this. So let us take straight away a problem on this. A Pelton turbine is to be designed for the following data. Power. Please note that at any time when they give power is equal to, it means it is only shaft horsepower, 9,560 kilowatts. You can convert 9,560 into 10 to the power of 3 watts. Then he has given head is equal to 350 meters. Very good. Speed is equal to, head means h. Speed means how much, what it is, 750 rpm. It is nothing but n. Then overall efficiency is equal to 85%. Then jet diameter should not to exceed 1/6 of wheel diameter. This is one more condition. Then CV is equal to 0.985, KU is equal to 0.45. So what is to be determined? Determine what? Wheel diameter, that is capital D. Diameter of jet, that is small d. Then number of jets. Then fourth one is, that's all. Three only, gentlemen. Let us take how to do it. First, what is the thing wheel diameter he is asking? Wheel diameter. Wheel diameter D is equal to 60 into U by pi n. Am I right? Because U is equal to pi d n by 60. From this we can get this. So what is U is equal to KU into root 2 GH. KU how much he has given? 0.45 into 2 into 9.81 into H is 350. Right? This is over. U is obtained. So already N is equal to How much RPM? 750 RPM. So substitute it direct. So therefore D is equal to 60 into 0.45 into 2 into 9.81 into 350 divided by 5 into 750. So if you solve this, you are going to get 0.95 meters over. Then next, second one, dia of jet. See, that fellow has given basically d by the ratio of d by d should be should not be more than 1.6. So I am equating it to 1.6. This is given. So therefore, D is equal to, calculate it actually, small d is equal to, right, 0.95 divided by 6. So it is 0.158 meters. This and one, then third one, everything is given. Number of jets. Number of jets, what we will write? Total discharge by discharge through each jet. So if I take like this, first to calculate total discharge. How I can get the total discharge actually? The total discharge is equal to eta 0 is equal to shaft horsepower divided by gamma QH. So shaft horsepower is equal to how much they have given, 956,860 kilowatts. Immediately into watts I have converted. Gamma is 9810 into Q into H is equal to 350. So therefore Q is equal to, and this is eta is equal to point, how much they have given, 85. So therefore Q is equal to, how to get it, 9560 into 10 to the power of 3 by 9810 into 0.85 is efficiency into 350. So how much you are going to get? 3.27 meter cube per second. So Q is on. Then discharge through each jet. Discharge through each jet. So discharge through each jet, if I take it, it is nothing but small q is equal to pi by 4 d square into V1. So pi by 4 into d is 0.158 whole square into V1 is equal to, how much we got? V1 is equal to initially, V1 is equal to CV into root 2 GH automatically. So this will be CV into root 2 GH, right? So therefore pi by 4 into 0.158 square into CV is 0.985 into 2 into 9.81 into 350. So if you calculate all this, you are going to get small q is equal to 1.6 meter cube per second. So number of jets is equal to number of jets is equal to capital Q divided by small q. Capital Q is how much? 3.27, right? Divided by 1.6. So it will be approximately 2 jets. So this completes as the, so any problem will be in this fashion only. And if any other type of problem is there, that also we will take it up. So in today's class, what we have discussed, if you take it, for what we have totally discussed in today's class, only working proportions of Pelton wheel, and followed by the design of Pelton wheel, and followed by basically a problem we have solved. So this completes to me the Pelton turbine, the theory portion. One or two problems I will solve in the next class. With that, we will stop this Pelton wheel and go to the next type of turbine. Okay. Thank you. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.